So this module will help you better understand how waves work. We're going to be going over some of the terminology, and if you follow along while drawing, you'll be able to retain the information possibly better. But before we get to drawing, I wanted to spend a few moments just looking at this animation that I pulled off the web. This is an animation of particle motion in a wave. And what you'll see, and you also saw in the videos, was that the motion of the surface was circular. Circular, and that what we have in the waves were known as orbital waves. So this is going to be a list of wave terminology. This will be posted as well on the Canvas/Blackboard page. But what I find more useful than having this up is having a diagram. So we're going to get to diagramming. So we have our generic wave. And we're going to look at the anatomy of a generic wave. So the top of the wave is known as the crest. And this wave has actually two crests, or the system waves. Crests. And the bottom of the wave is known as the trough. And again, I also drew this wave as having two troughs. So the first thing one tends to want to measure when looking at a wave is the wavelength. Wavelength is measured in one of two ways. You can either measure crest to crest, or you can measure trough to trough. Either one of these will yield what's known as wavelength. Like so. Then you're also going to want to measure the wave height. This is simply going to be your crest to trough elevation difference. And then finally, the last sort of measure of just sort of you can take with a still wave is the wave steepness. Steepness is simply your wave height over your wavelength. Now, for all waves, your steepness exceeds 1/7, your wave is going to break. It doesn't matter if it's shallow water, deep water. It does not matter if you're on an entire planet full of water. When your wave steepness exceeds 1/7, your wave will break. Well, gravitational is stable because at that point, the orbital motion is no longer sustaining it. Now let's take a look at a couple of the other features of waves that are actually, believe it or not, easier to measure, even if they're a little bit less easy to draw. The first thing we're going to talk about is each of these crests is moving, or troughs are moving at a velocity. The term for wave velocity, we call it celerity. This one, I've got a couple of videos where I can show you how I've measured it in the past. I will post those on the links in a moment. The other term that is often measured is frequency. Frequency. This is number of waves per unit time. Waves per unit time. And of course, a higher speed wave you'd think would have more waves per unit time, and it kind of does, but not exactly. We'll see why in a moment. Final one is period. This is just 1/frequency. It's just 1/frequency. This is the time between waves. So, with all these, you can use this to classify how fast a wave is traveling, how it forms, and a whole bunch of other fun. So a couple things that'll be useful for understanding waves. Wave frequency, again, is going to be the point velocity. Celerity, speed of wave, is the wavelength divided by the time. Now, I have some optional stuff. We're now going to watch a video of celerity. This is me running alongside holding my phone with steady camera. I want you to watch what happens to wave crest as we approach the shore. Point being, in this case, I can outrun the wave. Also notice how the wave crest evolves as we get close to the shore. That'll be interesting when we understand breaking waves. So, what I noticed was that the wave slowed down. And generally, the deeper the water is, the faster the wave can go. And that's the case as long as your water is less than half a wavelength deep. When you get into water that's half a wavelength deep or greater, what's going to control the speed of the wave is going to be the wavelength itself. And the speed of the wave is going to be proportional to the square root of the wavelength. Why is that? Well, a wave, remember, is being restored by, it starts with perturbation. All waves are perturbations restored by a force. In the case of ocean waves, that force is gravity. So let's put some gravity on here. So the green lines represent the restoring force. And you can see that at the crest of the wave, they're pulling down the wave very high. As you get towards that median water level, gravity's pulling a little bit less. Now let's look at the trough. So in the case of the trough, the gravity is actually pulling up very heavily. So the wave is pulling up very strongly. And so, but as you get towards this midpoint, you're getting a little bit less and less strength. So it's right at the midpoints, you get very little gravitational force. But at the crest or trough, you're getting a very strong gravitational force. Now, if this wave is traveling from left to right, let's take a look at what's going to happen when you add up all those forces into vertical motion. So the wave crest, gravity is tugging us hard, but it's not moving very fast. In fact, the crest is basically still. But as gravity tugs on things more and more, the downward motion is going to get stronger and stronger. And then here your upward motion gets stronger and stronger, and it's moving more and more and more upward. And so what you see is this sort of out of phase sort of behavior. Now, the longer your wave is, the more this sort of, right, so wave symbolized by the hands, what's powering all this is gravity and pressure. And so the longer the wavelength over which gravity and pressure operate, the faster your wave is going to travel. So we break down waves into three different categories. We have deep water waves, whose speed is entirely related to the wavelength and experience no friction with the bottom. Then we have our shallow water waves, where the water depth is less than 1/20th of the wavelength. In this case, the speed of the wave is going to be entirely proportional to the water depth. Now, when your water is between 1/20th and 1/2 of a wavelength, you get transitional waves. These are actually have characteristics of both. That wraps up our little classification of waves.